This video will teach you how to approximate area or integrals, since we now know that they're essentially interchangeable. We will be doing this using something called Riemann Sums. That's R-I-E-M-A-N-N. Riemann Sums. And there are three types. There are left, right, and midpoint sums. And then there are also something called a trapezoid sum that I will teach you how to do as well. Riemann sums are best taught with an example, so we're going to do a left Riemann sum. And the way that it works is we're going to approximate the area from 0 to 4 of x squared dx. Remember that this is the area under a curve. And I'm going to tell you that you're going to use 4 rectangles to approximate this area. So let's take a look at a graph and figure out how we do this. So here's a graph. Here's y equals x squared. I'll exaggerate it a little bit so we can see it better. And now what we do is, well, we have our interval from 0 to 4. So we have 0, 1, 2, 3, and 4. And whenever we do a Riemann sum, you want to figure out, okay, I'm doing 4 rectangles, and in this case they're all going to be equal length. So I need to break it up into 4 equal length rectangles, or intervals. So I have 0 to 1, like this, 1 to 2, 2 to 3, and 3 to 4. That's the first step. The second, and this is true for any Riemann sum, you want to basically break it down into the intervals, and that way you have the endpoints, etc. Now, we're using rectangles, so the area of a rectangle is base times height. The base of each of these is each one has a base of 1, because that's the width of each one. Now we have to figure out the height, and for the height, this is where we're actually going to use the function itself. So, for my first rectangle, do I pick 0 or do I pick 1? Well, the answer is I pick 0 because I'm doing a left sum, and so I picked the left endpoint. So I picked the left endpoint for each one of these, and I take all those and I plug them into the function. So 0 squared, guess what, is 0. 1 squared, 2 squared, and 3 squared. So this is going to be 1, 4, and 9. And if I draw a representation, the first rectangle essentially has a height of 0. The second one, I take the left-hand side and I go up to the function, and that's the height. The third one, I start at 2, because that was my endpoint, go up to the y value of 4, and there we go. And then 3, this is my last interval, go up to 9, over, and down. And so the approximation is approximately 14 units, and so we say that the integral is approximately 14. Notice a few things. First thing, this is obviously an underestimation, because notice that we have these green areas that we did not count. Okay, and so actually the true area, it has to be bigger than 14 because we've left off these areas here. That was a smiley face, but is actually a frowny face. Now, a left Riemann sum is not always going to under-approximate. For example, if you had a decreasing function like this, then the left-hand rectangles would actually over-approximate. So to figure out whether or not the rectangles over or under-approximate, you have to look at the function and think of it from there. Same example, but this time we're going to use a right Riemann sum. So here's the setup. Okay, exact same picture as last time, exact same integral that we're approximating, and the exact same intervals for this function. And I'm telling you that we're going to use n equals 4. This is the number of rectangles is what n represents. So my function got a little messed up, but that's okay. So same thing, the base of each rectangle is 1, just as before, because that's the length of each interval is 1. And then to find the height, instead of using 0, the right-hand side, instead of using the left side like I did last time, because it's a right sum, I'm going to use the right-hand side for each of my intervals. And so I just plug in 1 squared. So I have 1 squared, 2 squared, 3 squared, and 4 squared. When I add these all up, oops, that should be a 4, 9, and 16. And so remember that last time what I technically did was I technically did 1 times 1 because it's base times height to find the area. So 1 times 1, 1 times 4, 1 times 9, 1 times 16. This will give me a total area of 30. And so this area is approximately 30 using a right-hand sum. Let's draw it. My first interval went from 0 to 1, and because I choose the right side, that means the right-hand side is going up to meet the function, and then I draw a cross. So that's my first rectangle. For my second rectangle, same thing. The right-hand side goes up to meet the function, and then goes across. Third rectangle, and the fourth rectangle like that. Notice here that because the function is increasing, and we're using a right-hand sum, we are over-counting this much. And so the true integral value has to be less than 30. If we compare that to our previous left-hand sum, which was 14, we know that the actual value has to lie, like the integral value from 0 to 4 of x squared dx has to be less than 30 and bigger than 14. Okay, it's not a great estimation, but hey, it's not 2 or 7 or 400. So cool. We're going to now do a midpoint sum, exact same setup, so copy it all down again. Same setup as last time. We have 4 rectangles. We're approximating the same integral, and now we're using a midpoint sum. And so, sorry, just like before, the base of all of these is 1, because that's the length of each interval. But now for the height. Remember, for a left-hand sum, I'll use the left-hand side of the interval. For a right-hand sum, I'll use the right-hand side of the interval. So guess what? For a midpoint sum, you're going to use the middle value for the interval. The first interval goes from 0 to 1, and so the midpoint is at 0.5. But then I have to find the height, and so the way I find the height is I take the x equals 0.5 and I plug it into the actual equation. And so my height is 0.5 squared. Then for my second one, I'll have 1.5 squared, because 1.5 is the midpoint of 1 and 2. For the third one, I'll have 2.5 squared. And for the last one, I'll have 3.5 squared. And when I add all of these up, again, 1 times 0.5 squared plus, I'm basically just adding up these rectangles when I multiply them. And this gives me a value of 21. And so this integral is approximately equal to 21 using a midpoint Riemann sum. When I draw this, it's going to be drawn very similarly. First rectangle is like that. Second one has a height here, and so will look like that. Third one, like that. Fourth one, like that. Okay? And now notice, I'm doing a little bit of both. I'm overcounting here, and here, and here, and a little bit there. But I'm undercounting these other, and so they're sort of like bow tie regions. Okay, but you see that for every time I overcount, I'm also undercounting. So this is actually a pretty, it's probably more accurate than a left or a right in general, but it's also harder to do because you have to do a little bit more math to get these decimals to work out. Now, on a question, it probably won't ask you whether or not the midpoint is over or under approximating. If you want to think about it, you can, but that's probably not going to be something that I will ask. As an important note, the midpoint sum is not the average of the other two. So if we notice here, 21 is not the average of 14 and 30. And in fact, the trapezoid sum is the average of the left and right, but the midpoint is not the average of the left and right. Speaking of trapezoids, let's do it. Different problem this time, so don't copy it down. Well, copy it down, but like the actual thing that I'm going to write. Let's say we have a chart. So this is a different format, but let's say that we have a continuous function. So we have x, f of x, and we just have a few values. So 0, 2, 5, and we'll do 9. And then the y values, we'll say 3, 5, 8, and 13. Okay, just to give it a little variety, I guess. And we're going to use trapezoids. We're going to use 3 trapezoids to approximate the integral from 0 to 9 of f of x dx. Remember, integral is area, so we're approximating area. You'll know when you'll have to use trapezoids because the problem will say use trapezoids. That's basically it. What we're going to do for this is draw a picture. So here are my axes. I have, let's see, 0 to 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so there are my x and y values. Now plot the points. So we had 0, 3, 2, 5, 5, 8, and 9, 13. Now, an important thing to notice about charts is that you don't know and you cannot assume what the function is doing in between the 2 points. So for example, the function could look like that, or that, or that, or that, or that. That's sort of a function, probably breaking some rules there. But for the most part, you don't want to assume what the function is looking like. However, for trapezoids, you basically play connect the dots when you do the trapezoid approximation. And so what we do is we say, well, straight line, straight line, straight line, and then we drop down verticals at each of the values on the actual function. And so now we have 3 trapezoids. I'll color code them. So we have a blue trapezoid here, a red one in the middle, and a green one on the outside, this really big one. You might want to remember the area of a trapezoid, and you probably learned it as 1/2 base 1 plus base 2 times the height. Unfortunately, these are sort of like vertical trapezoids, so you might want to rethink about your trapezoid formula as 1/2 h1 plus h2 times the base. And that'll be a little bit easier to think about. So, let's do it. First trapezoid, blue, 1/2. The first height is the left height, which is 3. The right height is the second height, which is 5. And guess what? The base, the length of the base, is 2. Then we have the second trapezoid, easy, 1/2. The first height is 5. The second height goes all the way up to 8. And its width is 3. Done. Easy. Plus 1/2. This height goes all the way up to 8. And this height goes all the way up to 13, so it's sort of big. And this width is also big. It's, I believe it's 4 wide. But now for your answer, you just add it up and you do the math. So we have these 1/2s will cancel, the 1/2 and the 2 will cancel. 1/2 times 4 is 2, and then we'll see. So 3 plus 5 is 8. Here we have 13 times 3, which is 39 over 2. And 39 over 2 is, what, 19.5? And then the last one we'll have 21 times 2, which is 42. And so our final answer will be 69.5 units squared. And recall that this is the approximate value of this integral using only the values in the chart. For those who like expert level, you don't have to draw the picture. You can just do it straight from the chart. Interval 1, 0 to 2 is your base, and then height 1 is 3, height 2 is 5. Second one, interval is from 2 to 5, so the base is 3, height 1 is 5, height 2 is 8. Last one, 5 to 9, interval has a base of 4, height 1 is 8, height 9 is 13, and you just write it all down from there.